You know, when you crack open just about any piece of electronics, you're going to find a few core components that are, well, the absolute building blocks of everything. And the diode, it's one of the big ones. At its core, it's just a one-way street for electricity. Simple, right? But what happens when that simple little street gets hit by a tidal wave of voltage? Well, that's what we're here to find out.
So yeah, that's the big question we're going to tackle today. We'll look at how a diode is supposed to work, but honestly, the really fun part is pushing it way past its limits, into a pretty dramatic failure called reverse breakdown. And we'll even see what happens when things start to get a little heated.
All right, so before we can break a diode, we probably ought to understand how it works. And to do that, you have to look right at its heart, something called the PN Junction. This is literally just where two different types of semiconductor material, a P-type and an N-type, meet. And that simple connection, that's where all the magic happens. What's so cool is what happens right at that meeting point. See, electrons from the N side get pulled over to fill these empty spots, or holes, on the P side. This creates a really thin neutral zone right in the middle called the depletion region. Think of it like a natural barrier, a built-in gate that just stops electricity in its tracks. This little region is the entire reason a diode is a one-way street and not just a regular old wire.
So because we have that built-in barrier, we can actually control the diode in two totally different ways. We can bias it, which is just a fancy way of saying we can decide how to hook up the power. These two paths are called forward and reverse bias, and they are the absolute key to how a diode operates.
And it's actually pretty simple. Forward bias is like giving that gate a push in the right direction. You apply voltage in a way that helps current flow right through. Reverse bias, well, that's like trying to push the gate closed even tighter. The voltage gets applied in a way that reinforces the barrier, blocking pretty much all current.
And this here shows us exactly what's happening on a microscopic level. So over on the left, with forward bias, the voltage is literally shoving the things that carry current, the electrons and holes, toward the junction. This squishes that depletion barrier, making it super thin and letting current pass. But on the right, in reverse bias, the voltage does the opposite. It pulls those carriers away from the junction, which makes the barrier even wider and stronger. It basically slams the door shut.
Now this graph, it's called an IV curve, shows us the whole story in one picture. As we crank up the forward voltage, you can see not much happens at first. But then you hit this magic point. For a typical silicon diode, it's around 0.7 volts, and boom, we've pushed past the barrier. The gate flies open, and the current just takes off, increasing like crazy. It's almost like flipping a switch from off to on.
Okay, so we've got forward bias down. Easy peasy. But what about reverse bias? We said it blocks current. But what if we just keep pushing? What if we apply more and more and more reverse voltage? Well, that's when we get to the really exciting part.
Let's flip back to that IV curve and look at the other side. As we increase the voltage in the reverse direction, the current is basically zero. A tiny, tiny trickle, but for all intents and purposes, it's zero. The diode is doing its job perfectly. But then we hit a critical point, a wall. It's called the breakdown voltage, or VBR. And in that one instant, everything changes. The dam just breaks.
I mean, a tiny, practically non-existent current suddenly becomes a massive, uncontrollable flood. How on earth does that even happen?
It happens because of a wild chain reaction called avalanche breakdown. So first, that super high reverse voltage pumps a few stray electrons full of so much energy they start rocketing through the material. Then, these super-fast electrons slam into atoms, knocking more electrons free like a cue ball breaking a rack of pool balls. And finally, each of those newly freed electrons gets energized and does the exact same thing. It's a cascade, a literal avalanche, that creates this tidal wave of current flowing the wrong way through the diode. Now, there's another way this can happen called the Zener effect, but this avalanche, this is the violent, high-energy one we're focused on today.
Okay, so as if a full-on electronic avalanche wasn't dramatic enough, let's throw in another crucial factor that changes absolutely everything: temperature. These characteristics we've been talking about, they're not set in stone. They are incredibly sensitive to heat.
Take a look at this graph. See the blue line? That's our diode just hanging out at room temperature. But that pink line, that shows what happens when we turn up the heat. You can see the whole curve just shifts over. Both the forward and the reverse behaviors get all messed up. So what does that shift actually mean for us? Let's break it down.
So here's the bottom line. When a diode gets hotter, all that extra heat energy just makes it easier for current to flow, period. In forward bias, that means the voltage you need to turn it on actually goes down. And here's a cool number for you. It drops by about 2.5 millivolts for every single degree Celsius. And in reverse bias, that tiny leakage current we saw before breakdown, it gets bigger. Heat literally makes the diode leakier, which can be a huge problem if you're not planning for it.
So, we've seen how a diode works, how it breaks spectacularly, and how temperature can throw a wrench in the whole thing. But why is all this so important to know? Why does it matter?
It's because in the real world, circuits aren't in a perfect lab. They get hot. Voltages can spike unexpectedly. If an engineer doesn't pay attention to that breakdown voltage, a random surge could trigger an avalanche and just fry the component. And if they ignore temperature, a circuit that works perfectly on the test bench could fail miserably out in the field. Knowing these limits, it isn't just good design, it's everything.
Which, it brings us to one last really fascinating thought. This whole avalanche breakdown thing we've been talking about, it's usually a complete disaster. It's something you want to avoid at all costs. So if it's so destructive, why on earth would we ever design a component to do it on purpose? The answer to that question, well, that's the key to a whole other world of electronics, where we can actually turn failure into a powerful tool.